Morning. How are you? Good. How many of you here today? 61 and 4. How was your weekend? Okay, this is very hot, so I took off my jackets. I hope it is okay for you. Right? And then this week will be the last week. So, you know, Wednesday class will be the last lecture. No more lecture anymore. Very good. Great. Thank you, Hannah. So let me check the schedule first. Today, you need to submit the homework number 5. So last homework you should submit until tonight. So please submit homework number 5. Okay, any problem on your homework? Great. And then we will discuss about the Turing machine design. How can we construct the Turing machine for particular operation? Benjen, what do you mean? Okay, so we will discuss how can we design a Turing machines. Because sometimes you can do for the language acceptors. There is the transducer, language transducer. So acceptors we can produce yes or no outputs. Transducer we can convert input to outputs. So any computation can be done by the use of the Turing machine. So we will discuss how can we construct the Turing machine. And then Wednesday, which will be the last lecture. So hope you come to Wednesday as well. And then if you want to take contests online, then please send the requests and send an email to TA. Right? You know the address of TA on the course syllabus. Of course, you know what is the course plan. Everything is on the syllabus, so you can check the address of TA's email. Right? Send an email to TA. So I wanted to take a test online because blah blah. Of course, one reason is the distance. If you are staying overseas, right, other countries, or if you are staying, far from Seoul, then you can suggest you want to take a test online. Of course, this morning I got an email from the student association, 종합생회. So they are worrying about some, infection, like epidemic can be the problem if we get all together in offline. So until today, the schools, suggestions offline test because of the fairness, and then with the preservation of the safety. So if school policies change, then definitely we will change. Otherwise, if you have some concern about safety problems, so you can suggest your own opinion, right? If you're worrying too much, but also we can provide enough, fairness during the test, and it is possible. It is possible. We have some experience of the quiz, and that there are some difficulties. So we will determine finally on Wednesday class. By the way, you can send an opinion about it's an online offline test to the TA. By default, until today, we have three rooms. One is 여기는 301. This is our classroom. You never been there in this semester. Sorry, but we have one space. There's a 301. We have another space 302. So we can use this room as well. 302. Okay. 여기는 생활관 third floor. This is a new space, right? A new classroom, so it's good. And the third one, we have three space. Third one is a science library. Science library 615. So this is big classroom. Actually, I know this is maximum 130 seats are available. However, it is safety. By keeping the enough space, you can stay here over 60, and that's 30, more than 30. I don't remember the exact number, but it is enough space to cover all of you to come together with enough space, after keeping the distance. However, you can anyway suggest your opinion to the TA, and then TA until tomorrow 2 p.m. Tomorrow 2 p.m. You should send an email to tomorrow 2 p.m. 2 p.m. Tuesday regarding your opinion about online and offline tests. Then we will determine how can we go. So by default, we need to take a test offline with enough space, and then some of you have some reason you cannot come to Seoul at that time, then you can send an email and request online test. Okay, and then we will do some tests. We will do some rehearsal Monday next week, and then finally exam will be done online offline together. Wednesday next week. So Wednesday next week we will do the final examination. Okay. Any question? Okay. Chairman's question is online test and so offline test. No. Same. This is some rehearsal. So we will do some examination. What kind of problem will occur? So because this is only the moment we can take a test. So we better do some exercise and some rehearsal Monday. So it is not a real test. This is only the examination. How about everything is okay for you? And if you want to use a smartphone together with the laptop, then you can do the test with the TA, and the TA will guide you how to prepare the real examination Wednesday. Okay. Other question? Okay, great. How about the weather on today's network weather? It says resolution is okay. Good. We are studying about the Turing machine. This is most powerful automata. Later on, we will see how we can, do any type of computation. Like can, do the implementation of computer algorithm on top of the Turing machine. So algorithm also, defined by the use of the Turing machine. It is also possible. However, Turing machine looks quite simple. You can see the one tape, and then one head, So exception is a two-way. You can move right or left together, and then you can read and write with the head. That's it. That's it. At the first glance, it looks even simpler than push down automata, but it is very powerful. You can implement any computation by the use of a Turing machine. So this is very interesting concept. Most important part is the delta function in Turing machine. Delta function defines how can we move for the next step. This is actually the same as the concept of program. Right? We are developing the program. Then how can we implement the program? So by the use of a high-level language, of course, we can implement the program. This is very powerful in principle because we can implement by the use of only the small set of instructions, small number of instructions. However, which adequate for doing complicated tests. 잘 보이나 모르겠다. Okay. So this is the same as the concept of a program. We can do, various types of computation, and we can implement anything by the use of computers. Then how can we develop our own program? There are, limited number of instructions, small number of instructions. In this case, move left and right, just change the symbols. There are only small number of instructions. Change symbol A into B, like alphabet A to B, and then, also table alphabet can be changed. So this, step is very simple. However, it is adequate. You can implement any task by the use of this Turing machine. So this is amazing results. Right? So we will see how we can do. So of course, this is formal description of the first Turing machine. So it can be described by the use of the transition graph. So this is also easier to understand. It's an intuitive way of description. So in this case, A is replaced with B. So the tape symbol is replaced, and then in case of B, you just move the heads without changing the symbol. So this is simple implementation. So as a result, AB blank is changed to BB blank. So we can replace A with B. So every A will be replaced with B. So this is a Turing machine. For more information, let's think about labels. Labels with different machines. In case of the finite automata, the label looks like here, alphabet A. In case of push-down automata, label looks like A, B, right arrow C. Then stack symbol B is replaced with the C. In case of a Turing machine, how about the label? Label can be A replaced with B and move right, or B move right. So this is the label we can put into the transition at the Turing machine. Okay, stack the tape is the symbol A in the tape in the input tape is replaced with B and then move right, or otherwise just simply move right without changing the symbol. So this is some label we can use. Okay. there's some word like a standard Turing machine, So it is, there are different definition of Turing machine. So we wanted to define the main features of Turing machine. So main features can be described in the standard Turing machine. So if you say this is a Turing machine, by default, it implies standard Turing machine. Later on, we will see there are some other types of Turing machine. So standard Turing machine looks like this. Unbound in both directions. So we can go here, or we can go there. So there are many cells, infinite number of cells we can store. Then we can put input here, and then all others are filled with blank. And the heads start from the first symbol in the inputs. So this is an illustration of the standard Turing machine. We have infinite number of storage, and then inputs is put into the tape, and then heads point out the first symbol of the inputs. So this is the standard Turing machine, and then by default we assume deterministic machine. But deterministic machine, there's no multiple movements. So this is standard Turing machine. So we will discuss how can we design one. Then one computation consists of multiple steps, and then each step can be described. So in case of Turing machine, it is called a configuration. For instance, if the Turing machine in the middle of computation and it points the value 1 here with the state Q5, instead of describing this situation with all the arrows, box, and then tags, we can simply write in the text like a text string. So it can be described like this: 110. Q5 point out here 1. So Q5 is current state, and 1 is the pointed by the head, and 1 is the remaining part. So this string 111 Q5 111 is equal to the illustration of this state of Turing machine. So this is a simple example how to illustrate one status of the Turing machine. So it is called a configuration. So anyway, so I will explain the concept, and then I provide some sample example of Turing machine that makes much easier to understand how to construct the Turing machine. Okay. And the next configuration, of course, determined by the delta function. So if next state become Qj from Qi, and then if symbol space with C, then move left, and we can define the next configuration is like this. From here, it will move here because state is changed from I to J, and then move left. So therefore, next position will be the A. So anyway, this is the example. How can we use the configuration? So configuration is from one state to another. So once this is we'll describe in the next step. Okay. First example is how can design a Turing machine for the language, for 0 0 star. Can be designed. Actually, this is one example. Can be designed like this. Another illustration by the transition function. So Q0, Q1. Then here we should check the first appearance of 0. So we should check here 0, case of 0, and move right. Move right. And then the remaining parts, no matter how many repetition of 0, so we can move right. And then finally, we can move into the accepting state. So here we can accept after checking everything, and then it should be the blank, and then move left, and then finish. Okay, here you may think about some situation like should we always check the blank, otherwise it is not acceptable? Yes, of course, you should check. The blank should appear after consuming all input symbol, right? If we see the symbol 1, it cannot be acceptable. So it must be blank. And then another question is, should we move left? Why not move right? So for instance, the input is 0, 0, and then it can be placed in the blank here and here. So we start from here, and then after reading 0, move right. So next here, after moving the move right here, and then because of a blank here, the next symbol is blank, and we will move left. So final position of head is here. So we will complete the computation. Then why not move right here? In case of move right, the head will locate in the blank, somewhere in the blank. So it is not recommended. So we'd better the head put on a one of the symbol in the string. So it is, you can do the next operation from the certain value rather than blank. So we'd better move the head into some location of the string. So this is the reason why we do the termination with the blank rather than move lights. Okay, good. Oh yeah, good, very good. Weather is good on your computer network, so that's very nice, very nice. Okay, and then this is acceptor, and then another type is transducer. Transducer is transforming the input into output, so we can do any computation. So later on we will see. Then let's try to design. So this is an example, and you can understand much easier way. Okay, first example. Design a Turing machine. So let's try to build a Turing machine with 3 states. Some constraints, 3 states that accepts. So it means we should design a Turing machine for acceptor. Language in a form of A plus B star over sigma A and B. Okay, then first mission is how can we design a Turing machine for the language in a form of A plus B star. A plus B star. Okay, then in this case, we can start from with A. First, the symbol should start from A, right? If this is first condition, we should check. And then next one, no matter what is following, so we can move right. Okay. And then if we see the blank, can move left. After that, finish. So this is the Turing machine. Okay. Not so difficult, right? It is similar to design a finite state machine. And only the different types of label, right? You can use the label of A, A move into the B and then move right to move left. So this types of label can be put onto the Turing machine. And then some of you may ask, how about the machine in the form of a move right, and then why don't immediately offset the string? Because no matter what is the remaining part, if we see A, then we can go into the offsetting stage. Of course, it is possible, but it is not recommended because we'd better check all the inputs over the alphabet A and B, and then we should put the head on at the end of the string or someplace on the string, and then the next one is a blank. So this is not recommended. So we'd better use this one and check all the input symbols and produce the results after checking the blanks, after reading every input symbol. So this one is recommended. Okay, then let's move into another example. So it is quite similar. W is even. Then how can we design? So A move right, B move right, A move right, B move right. We only count the number of symbols in the input, so they can move left. So if the input is even, then it can be accepted. So this is an example. Okay. The blank lambda. Well, lambda is empty string, but blank is tape symbol. We want to indicate the empty, nothing in the tape. So we use the blank as a tape symbol. So not exactly same as the lambda, but also it's similar in the similar to the representing the lambda in the tape. So but blank is particular symbol in order to recognize there is nothing in the tape. Symbol A, B, or this is a Turing machine. We should understand the Turing machine looks like this. And move left and move right. The head will move left and right. So we should have this operation. And in case of A is replaced with B, then A is replaced with B because we can write the symbol onto the tape. That's the unique properties of the Turing machine. So you should illustrate this situation. Then A, replace A with B and then move right. Can be write down like this. This can be the label of that operation of the transition. Okay, good. Then a more complicated case. Okay. Looks similar, right? The language here and the language here, even the language here. But what's the difference between these things? What's the difference? is to implement the acceptors. One thing is, of course, this is regular language. This is regular language. How about this one? In this case, is not possible by the use of the regular language. So this is context free. Anyway, this can be done by the use of Turing machine. We can accept any input in the form of A and B. It means the same number of A and B, not the arbitrary number of A and B. So the B needs to be the same number of A. Right? Then how can you design? By the use of only single tape. How can we implement this one? So we should understand this can be done by the use of concept of computation. Take a look. For instance, input can be located like A, B, B. Then it should be accepted. Then how can we do this? First, find A and replace with X, because we can write, right? So we can replace A with X, and then move right, and find B and replace with Y, and then move left, and then we find A, replace with X, and move right, and then if we find B and replace Y. If we move left and there is no more A, and if there's move right and no more B, then we can say the string is accepted. Then the problem we should check all A and B by the use of the only the one single tape. So this is the possibility of design a Turing machine. So first, you can think about the 3 steps one by one. Replace the leftmost A with X, and then find leftmost B and replace with Y. Okay, find leftmost A, leftmost B, and replace with X and Y respectively. The last step is no more A and B. B remain. Then accept the inputs, the input string. So we can design a Turing machine by the use of this concept. So then how can you do? After this, let's take a break. A, X, move right. Okay, this is the operation. Replace A with X and move right. One. Do something here. Skip A. Skip X. Later on, we need to go checking no more A. B, replace with Y, and move left. So we found the leftmost B and move left to Y, move left. A, move left. X, move right. Y, move right. 3 blank move left. 4 finally this is an accepting state. In case y we can move right. So that's it. This is Turing machine. Okay. Okay, so it looks like you're a little bit confused, but try to follow one by one. So during the break, you can think about how can you design. Of course, this is one example to design the acceptor for the language in A and B, but you can find another one. And this is not the only one. Okay. Now let's take a break and then let's continue. Of course, let's discuss further about your question after break. So 5-minute break. Let's continue at 11, 13. Break and think about how can we design the Turing machine like this. Okay. Break. Okay, let's continue. So there are a couple of questions. Cheon's questions are blank B or the label. Is this the label blank going to be or is possible? Yes, it is possible. We can write, like sometimes we can write another symbol at the end of string. So we can use the blank right arrow B in order to express, append B at the end of a string, of course. It is possible. I think we should add Y or to the statue. Y or is in relation to X or Y or so A X X Y X. Then we should skip. Right. YR. Okay. Let's think about. So, maybe you are right. So, that's a good suggestion, Cheon. Let's try to check. So, you want to show that string AABB is accepted. If the input AABB is entered, then definitely it should be accepted because it is in the form of A and B. Then let's check. Cheon, provide a good opinions. Probably we should care about Y in the middle. Let's just say. So by the use of configuration, we can start from the Q0 AABB. So this is the first configuration of the Turing machine. And then we can move into the next configuration. So it yields. So Q0, the first one is A. So replace it with X and move right. So what is the next configuration? Here? Move right. So X, Q, 1, A, B, B. This is the next configuration. So we move right and then change the states already after replacing A with X. Okay, and then what is the next configuration? Q1, next is A. So we should move right. So X, A, Q1, BB. Okay, so this is the next configuration. And then what is the next configuration? So next one is a B. So we should do something here. B replaced with Y. So move left. So we should do X, Q2, A, Y, B. Y, B. And then what is the next configuration? Next one is A here. So move left. So Q2, XAYB. Then what is the next configuration? X, move right. So X, Q0, AYB. This is next configuration. And then next one is the Q0 we replace with X. So X, Q1, YB. Okay. Next, Y. In the Y, we should move right. Move right. Right. Because there's no V yet, so you should have right? 채운. Great. 채운 right. 채운. Good. I will credit you definitely. 정채운, 채운. 채운, you already have full credit this course. Extra credit, extra points. Good. Johan, I can move after ABB. Chang, move right instead of X. Y is the X. Really? We don't need X. Probably, right? Maybe we don't need this one. Move X and then X, move right. And then move right. Okay. X. Right. Yeah, it is possible. Okay, so anyway, so they same points. 해찬, you did a great suggestion, but already 채운 fixed the problem. So that's good. Okay. Y X. Yongjin, you have the same opinion. Okay. 재창, Yongjin have the same opinion, but 채운 already point out that part. Okay. So and then 정환 is. Oh, okay. 정환, it was you. Okay, three of you have the same opinion. Great. We should fix with I move Y right arrow or. Okay, and then XSQ1 Y, and then you can move right. So XX Y G Q1B, right? XX Y Q1B, and then what is the next? XX Q2YY, nice. Q2YY, and then XQ2 XYY, move left, and then point out X. So in case of X, in case of X, we should stay here. Let's move right. Right. Q2YY is Q1 move. Replace with here, and the Q2YY move left. Move left. X Q2X move right. So Q0 YY, and then Y. Y move right. So Q3, we should go into the Q3 X Y Q3 Y, and then Okay, so y we should move right here. So x y q3, and then because of the blank, we should move into the state q4. So x y q4 y. So this is the end. So we reach the state q4. So AA is accepted. AA is accepted. Okay, great. Right, y moved or x or this is right. Okay. So while I wrote down in another notes, there was some mistakes. It was some mistakes. X move right necessarily because x move into right necessarily because it's right. X move in Qjar, right. So we should do this one, right. That's correct. Okay. Okay, great. So this is one way to design a Turing machine. So now we do for the acceptor. The Turing is an acceptor. Another one is a transducer. Transducer is we can transform input into output. Transform input into output. So we can do any computation. For instance, implementing function f like this. After getting input w, we can produce y prime. So this is the implementation of the transducer as by the use of the Turing machine. Okay. Then what is an example? So this is the design of Turing machine for the certain computation. Sorry. Design a Turing machine do the copy operation. So we want to do the copy. So more precisely, so we want to do the computation. What types of computation? U0 W. We start from this computation. Sorry. And you can get the results. Q, F, W. So this is a copy operation. So how can we design the computation? For instance, this is a simple computation. Just simply get an input W and then you can copy and get the WW as a result. WW, the basic operation. Then, so we should think about the first design of the Turing machine. So one thing is like, oh, if we get an input 1, 1, then we should produce output 1, 1, 1, 1. Then how can we do this? The input is 1, 1, produce outputs 1, 1, 1, 1. So there are several ways, but one way is like this. We can replace 1 with x, and then move it at the end of the string, and then create. Oh, sorry. Replace x and replace x. So replace all 1 with x, and then find x, and then replace with 1, and then we move into the end of the string, and then write 1, and replace x with 1, and then move at the end of the string, and then write 1, and then try to find x. If there's no more x, then we can get the result. There are several other ways. First thing is anyway, we replace every 1 into x, and then replace x into 1, and then that go into at the end of the string, and then attach 1 by 1. So this can be done by the use of the 4-step. Replace every 1 with x, find minus x. Replace with 1. Travel to the right. And create 1. So we can sketch the Turing machine. So this is the conceptual design of the Turing machine, and then we can implement this one. So let's try to implement this one. Then how can we do this? Q0. First we start from Q0. Then we can replace every 1 into x and move right. And then now we have a string of x, and then we will find blank, and then move left Q1. After that, we can do 1 by 1. We have x, so replace with 1 and move right. Then we can skip all 1. Then if we see the blank, then write 1 and then move left. Then if we have 1 and then move left. Move left. If you see x and then move right 1, replace with 1 and move right, and then travel all the x, all the 1, and then attach the creates the 1. And finally, if there is no more x, we cannot find any more x, then move right. Then we can accept. Okay, so this is one Turing machine. Okay, this is the implementation of the design of Turing machine here. So we can implement this one. Then, of course, this is not only one. So we can design another way. Someone like this one. Then replace with X and go into the end of the string and then write down here Y, and then come back again, replace 1 in the X and then attach the Y, and finally replace X and Y into all 1. So this is another way. So this is a simple sketch. Y1 or X. This is only for your reference. I wanted to say there's no, there could be multiple Turing machine for the same operation. Of course, the different steps, but we can get the same results. So this is another Turing machine for the copy operation. Okay. So of course, the third one is possible. So we can design by ourselves. Okay. Then, any question? All right, Juhan, that's a good question. So by default, inputs, and then everything is filled with blank here. So if we put something here, the next one becomes blank. That's correct. Okay. Great. So it looks like quite complicated, but we can sketch the high-level description of the Turing machine, and then we can describe that one into the Turing machine by the use of the proper states and the transition with the label. Left alphabet by X blank, or can we? Which one? Kyungju. Which one? Remove left alphabet blank. Leftmost alphabet. Blank A is possible. And I think you want to write here. Of course, we can write here something. Right? We can write. Yeah. Kyungju, it is possible. Sometimes you can instead that Turing machine allows infinite left and right. So you can write here. Right? You can write here. So of course, some of you suggest a solution like instead of the attach here, additional one here. Someone suggests here or here, or either way is possible, right? That's possible. Good. Then let's move with this. In this way, we can design any computation by the use of a Turing machine. Of course, sometimes can be the big Turing machine. So anyway, if we wanted to say the Turing computable, it implies there is a Turing machine for the computation. So if we do FW function, then if there's a Turing machine for that one, then it is called a Turing computable. So computation means it can be carried on in carried out in the Turing machine. So it is same as a computable. Right? This is sometimes omitting the Turing computable is the same as a computable. And then we need to understand the difference between Turing recognizable and Turing decidable. In case of Turing recognizable, there is some Turing machine. Then we can say that that is a Turing recognizable. In order to say that the Turing decidable, it means every input should be determined. So it implies there is no loop. In case of Turing recognizable, sometimes it allows a loop. It cannot be finished. Sometimes accept or reject, but some inputs may continue the operation forever. So in that case, it is possible by the Turing machine. So it is recognizable. However, Turing decidable means there's no loop. Always, whenever we get the input, we can determine accept or reject. So it is Turing decidable. Which language is bigger? This is called actually recursive enumerable language. We will discuss later in the next chapter. Recursive enumerable language. This is recursive language. Recursive enumerable. This is a superset, of course. This is superset, and this is subset. This is superset, and this is subset. Because in order to determine every input, it needs to be the subset of the Turing recognizable. Because if there's any Turing machine, then the language can be Turing recursive enumerable language. Okay. And then some cases we cannot design very complicated tasks by the Turing machine. So in that case, there's an additional way. One is the use of high-level description. You can use a block diagram, or you can use a pseudocodes. For instance, this is some concept of encapsulation. This is the high-level description of the Turing machine. So this is another Turing machine. This is one of the Turing machine. Then this is high-level description. It means each component already can be implemented by the Turing machine, and then we can combine together. So, for instance, if we want to compute the function with x and y, if x and y is plus, if x is bigger than y, and otherwise we want to put 0 if x is less than y, then this computation can be done by the use of this Turing machine. So this Turing machine illustrates the computation plus y0. But in order to accomplish this operation, we should have the comparison and then addition. So the comparison addition can be implemented here. If x is bigger than y, then we do addition. If x is less than y, we can erase everything, and then result becomes 0. So this is one of the illustration, high-level illustration. Another one is a pseudocode. Also, it is possible, as like we already discussed in conceptual design. Anyway, so this is high-level description of Turing machine in order to implement the more complicated tasks. Then this is one example of the pseudocode. So in order to do the multiplication of the two integers, and we can do like this. copy operation, of course, should be defined first. Let's say. So this is how can we design the more complicated tests. Then the next lecture we will discuss the lambda calculus and then the the another types of Turing machine in the next class. Okay. Any question? Can be put onto the you point out the current symbol and then light string, not the light string. It's point out the current string, and then in the configuration, in the description looks like the next one. But anyways, it has the header point out the symbol in the tape. Okay. Okay. Good. Thank you for your participation. So next class will be the last ones, and then I hope to check the last attendance because we only checked once. So hope to see Wednesday. Thank you for your participation. See you Wednesday. 수고 많으셨습니다.